Hello everyone, my name is Abdullah and I go by Falafel Online. And today I'm going to be showcasing my new game engine called Fado Engine, which I made almost entirely from scratch in C Style C++ and with Direct 3D 11 as the graphics library. And what you're seeing now is the demo that comes with the engine, and you can download that over in GitHub. I'll leave all the links in the description. So when you download the demo, you'll have two builds, a release and a debug build. And if you just go and open the exe, you'll have this. And by the way, immediately you can see that we have like a movable window, and we can alt enter to make it go full screen. And so let me first unmute the game. There we go. So this is the 3D level showcase with the engine. You can move around with the controller or with your keyboard, and you have these objects with interesting materials, I should say, and you can like bump into stuff. If you hit things or collide with them, you'll hear this SFX. And you might have already noticed that if I actually raise the volume a little bit, there's this fire sound going on this red cube, and it's completely 3D. Like if you're wearing a headphone, you should be like noticing the difference when we move around this cube. And you can see we have some simple but interesting materials, like we have some textures with colors and transparency. We have regular colored textures, and we have just also blank textures with some light calculations going on. Lastly, there's also the particles, these blobs flying all over the place. And there's a simple skybox with an infinite plane. Let me go ahead and turn the volume down a little bit. And if you click P, you will see this beautiful looking menu where you can save a level, load a 3D, 2D level, or you can switch camera. And switching the camera will switch it to an orthographic camera. This is what you would see in a 2D game. Let's switch it back. And also we can save the level, which we will see later. And lastly, we can load our 2D level. And you'll see this beautiful looking falafel going on here. We have this cute sprite animation when you run. It's like Sonic, but with the big head. And a simple idle animation as well. And we have also 3D sound here with this cube. And you can move stuff around. You can bump things into each other as well. And yeah, it's just a simple showcase level. Same thing here, although switching the camera wouldn't really make much of a difference here because these are just quads. They're not really like 3D cubes or something. And since we saved our 3D level, if we go ahead and load it, it will go back to the same position we were with all like the entities moved and everything. And this is the release version. So if we click exit, we can go back and test the debug version. And the debug version is the same level, but you'll see some debug lines going on here with different colors. I'll explain those in a bit. And we have some MGUI menus. The FPS is capped at 60. This is all intentional. We can change the position of the camera if we want. We can change some of the light attributes. So I think this is the most visible one. So like if I change the direction, you can see the shadows, not the shadows, like the light on the object changes. We can change the colors. You can immediately tell that I know what I'm doing here. I mean, look at this. This is some next gen graphics. I mean, come on. It's beautiful. And the debug lines are essentially like the collision types, but I will get into that later when we're explaining like the systems. But essentially like the blue one is almost a static one. Like I cannot move it. When I bump into it, it pushes me back. Whereas these two, they're like more dynamic. I can push them around. They can push each other around. But I'll explain all of that in detail later. Same thing with the 2D level. You can see now the bounding boxes. And there's like this cute thing where you can see that things kind of bump into each other, go into each other for a little bit, but then go back. I like this. This is somewhat intentional. So anyway, these are the showcase levels that come with the demo. And now, let's go into the technical stuff. Let's open up the code. Actually, as a matter of fact, you can download the code immediately from the repo in GitHub, and I'll go ahead and just download it and build it to show how easy it is to actually build this engine. So if we download the zip, just I'll put it on desktop. There we go. If I extract this, of course, assuming that you have a C++ compiler already installed, if you go inside here, go into Fado Engine, and then just click this build batch file, and yeah, you can trust me on this one, and boom, we have the solution. And I assume if we go in here and we click Ctrl-Shift build, it will build it, and we can run it. And there you have it. You have the Fado engine installed and ready to build from the source code on your machine. Okay, so let's go into the technical side and we'll start discussing the engine and every part of it, almost. Okay, it's worth mentioning, I have a full documentation of the engine on my portfolio. I'll also leave a link in the description. But yeah, it's a great place if you wanna just look around and see like how the engine is made, or if you just want to use it as well. Okay, so when you launch the solution, you'll find two projects: an engine project and a game project. So the way that things work in the engine is that the game itself is in a different DLL project. This allows us to essentially hot reload stuff. So like if you change things in your game while the game is running, you can just recompile and things, or hot reload, and things will update there as well. But we'll start with the engine. So we have a platform layer, a Win32 platform layer, and this is where the engine starts. It's our main function, our Win main function. There we go. So the way things work in the engine is that essentially when our main function starts, we allocate all the memory that we need in the engine, in the game entirely, and then we just reuse this block of memory as many times as we want. This essentially removes the need of any dynamic or heap allocation, anything of that sort. All of that is out of the way. You have a memory block and you're just reusing it, and when you exit when you return, essentially when you exit your program, it just gets wiped. So there are essentially no memory crashes in this engine, which is such a flex to say. I mean, and of course I'll explain the arena and everything going on here later. But essentially we're allocating everything we need. We're setting things up, the game state, the renderer, and all of that. And then we have our game loop. And in every frame we update our delta time. And then we check if we need to hot reload the game. This is like checking the DLL. And then we take the input, we process the input and update it. And then this is the one function from the game layer that gets called. It's the game update function. So we update the game based on the input. Then we render, and then we update the sound. And lastly, we just we refresh or we copy the state of the input from this frame, so we can compare it with the next frame. And this is simply it. The window itself, when it comes to Windows, it's just a regular Windows window. I do have some I do have some custom stuff when it comes to toggle screening, but honestly I copied this code online, so like I can move stuff around, scale up and down, and up, and we can go full screen. Okay, so going back to my glorified documentation, The engine is essentially made of three major parts. The platform layer that I just showed, where essentially everything gets initialized, and then we have a renderer and we have a game. And I'll explain this shared stuff later. So I'm gonna start with the game because it's mostly just logical stuff rather than the graphics stuff we'll get into when it comes to the renderer. All right. So our game layer, you can see that it's actually quite small. We don't have a lot going here. We have like two files, a collision, CPP, and then input and levels. So we'll go into our Fado file. And by the way, I forgot to mention, this engine is very data oriented. I don't have any classes at all. I only have one instance where I actually inherited, which I'll showcase in a bit. It's just structs. We have structs and we just operate on them. No classes whatsoever. The way I look at it, if the code is simple, easy to understand, and efficient, then there's no need to complicate it. So in our game, we just have this one struct. We call it our game state struct. We have our input, something called shared stuff, our sound manager, our level, a font, and then just some camera camera rotation stuff, and like our game state flags. And we have one function, this function right here. This is what gets exposed to the engine layer. The rest is just in here. It's all internal. But before I go into that, I do want to mention this shared stuff. So since our game and renderer are separate, or like in separate projects, things might get tricky when you need to use something in both of them. So I literally just made a file called shared, which is the struct of shared things that both the renderer and the game, or I should say the engine and the game, might need to read or write into. And this is it. Like, it has the camera, our light, and it has like the assets handles. We'll get into these later. Essentially, like the entities, the transforms, everything that they might need is just in here, and they can just access it. I think it made things much easier. I don't know if you call this singleton or whatever, but it's really convenient and it's self-explanatory. Like the name just, I called it shared stuff and it just stuck. With that in mind, I should also jump into this file, because this is the file that almost every file in this engine includes. It's the main like Fado types. So you might have noticed in some of the code that I have this Fado debug in some areas in the code. So the way this engine works, it's always the same build. Like, yeah, I do switch the debug and release when I wanna create the final version, but it doesn't really change stuff in the engine. It's just like Windows when it comes to this. For me, for the engine itself, we just add this Fado debug if we want stuff to be in a debug version. And that's it. And then I have all my type diffs, so all of your integers, your unsigned integers, and everything. And I just went crazy. Like, I even went to the character. The beautiful thing about working on your own project is no one can tell you what to do. So yeah, I decided to call a character a C8, because why the hell not? And then you got like definition of some of the main structs, like the math structs here, the vectors. They're defined here because they're used all around, but in our math, our custom math file, where is it? There we go. This is where all of the actual like math overloads and functions are here. So they're just defined or declared in Fado types. So in here you have all of the types that any file might need to also know, and they're essential to the engine essentially, and we'll go into that in a little bit, but I thought this was worth mentioning. So going back into the game layer, if we go into our CPP file, let's go all the way down. This is the game update function. It is as simple as that, as you can see. So what we're doing is we're essentially initializing the game if it hasn't already been initialized. and then we load a level, which sets our current level, the game state's current level, and then we're just updating the level. And this is like shared stuff, like the UI for the demo, I just put it in here. And this brings us into the level itself. So the way I went about levels, a level is just like a name and three functions. It has an initialize, a begin function, and an update function. And this is the only instance in the engine where I actually used inheritance. So a new level, like if we go into our 3D level, it is a level and with all of the entities, like the entity handles that it has in the level. The reason I did this because like the current level from the game state perspective, it doesn't need to know about any of the entities it has or whatever is going on inside. It just needs to know about these functions, or at least even the update only, you could say. So whenever a level gets created, it inherits from the main level struct, and then it has this help this helper function where it just assigns each of the function pointers to an internal function in the file itself. So like we have our 3D level showcase in it, and we have our update and our begin. And so simply the game layer would just call the update, and whatever you have here assigned to the update function, this is what will get triggered. But yeah, essentially it's that simple. A level is just these three functions, and of course like you can go crazy. You can have multiple layers and whatever you want. You can do the whole game in here. And that's the game layer in short. We'll get back into like some of the stuff in here, like the input, the loading, and all of that. But yeah, simply this is it. It just has some level and it updates the level every time and does what it needs to do. So upon editing this video, I realized that I had skipped over a major part, even in my documentation, which I'll probably add later, but I'm gonna just mention it now, which is the input system in the engine. It's actually really straightforward. So the way that things work is, first of all, we have our buttons. Our button is essentially just these values. Was down and is down, and how long has it been held for. And then, based on that, we have our mouse input, which is just a bunch of buttons, and then its position, whether it's moved on the screen, the last frame, and whether it's rotating. This is just for the 3D camera that I have. And so, using the buttons, we have our controller, which has just a bunch of buttons. And also we have some stuff for an actual controller, like a PlayStation controller, values for the left and right stick, and also the left and right trigger, like how hard you're pushing a trigger button. And so the way that I have these here is I have some like general names that can be understood regardless of which controller you're using. So D-pad buttons, and then like the other side, the buttons on the right, like on PlayStation, the triangle, circle, X, and square. These are what I call action buttons. So action up, down, left, right. Then you have your shoulder button, your trigger buttons, the two like options buttons, and this is just for the size, so it doesn't matter. And so our input is essentially just a bunch of controllers, a keyboard, and then supports up to 4 controllers, even though I don't really have a co-op game, but if you have multiple controllers, all of them can add to the input. And we have our mouse input, and then input mode, which is just something handy I made so that in the engine now I can rotate, but if I click pause, I cannot rotate any longer because I'm in the UI mode. So it's just something handy. And then your delta time. And so what happens in our platform layer, every frame, we first process the keyboard input, which is just here. So the way I do things is that regardless of whether you're on keyboard, you're on controller, all actions that you do should be mapped to one of these buttons. So for example, if I'm clicking W on the keyboard, I make it so if it was like you're clicking on the up on the D-pad on your controller. So I update the D-pad up button instead of some hypothetical W button. This way, input for the keyboard and for the controller can all be can be unified. And it's just as simple as that. The way that things work here is that we check from our Windows L params if a button is being clicked this frame or if it was clicked the previous frame, and we update that on the button itself. And if a button was down and is currently also down, then that means it's being held, so increase the held time or the held length by delta time. And that's it. If it's not, then we reset the held length and it's just not down anymore. And for our controllers, it's very similar, except here we use X input. And first of all, I'm doing a bunch of stuff for the camera rotation. Essentially, we're checking the delta each frame if the camera has moved or not, but also if it has moved within the bounding boxes of the engine. So for example, this prevents that if I'm rotating like this and then I exit the window, if I go back here, the delta technically is from here to there, so it's gonna snap. So instead what I do is, if we just go out of the window, I just zero it out and reset the thing. Anyway, and then we update the mouse buttons similar to the keyboard. And then lastly, here's what we do with the controllers. So we iterate over our controllers, and for each controller, we just check the button state. For example, the gamepad A here, we check its X input state, which will result in us knowing if it's being pushed down or not, and then we just do the same like we do with the keyboard. We're just updating an F game button state. And for the triggers, for the triggers and analogs, we're doing something similar, except we're updating floats for X and Y values. And essentially that's all that the window platform layer is doing. And then back in our input, before we go into the game, I added some helper for the stick to check whether it's being held in some direction. So I added an enum, like a stick direction, and based on the X and Y values of the stick, you can check whether a certain stick is being pushed in some direction. But anyway, in our game itself, if we go, for example, to our 3D level, so in our update or handle input, we just check essentially the states of certain buttons, and based on that we decide what to do. Also, I had these helpers as well. I have these helpers which just check if a button is pressed, meaning if it wasn't down and now it is down, so it's just been pressed. If it's been down for some time, if it was just released, and if it's not being pressed at all. They're very helpful, so instead of always having to write this or this, we just actually check the thing. Like for example here, all I care about if it was down or is down. Like if the player was holding or clicking the D-pad up button, then I just wanna move the camera forward. And with the sticks, you can do something similar. So here, if I'm using the controller, this is a camera rotation. And yeah, that's pretty much it with this simple framework. I mean, you can pretty much do anything. You can even do like the like combos and stuff technically. So it's pretty simple and it's working for me now. And yeah, that's input. And with that, we will go into the renderer, which is this guy. So this file, it has everything DX11 related. It's only in here, so no one outside of this knows what an ID3D11 renderer target view is. Just this class knows, or this file. We have all of the structs. This is like the main D3D struct with all of the essentially everything DX11 related. And then we have our shaders. We have a main material shader. This is the shader that is applied on all of the entities. We have a particles shader, and then a UI shader. And for now, that's all of the shaders that we have. Only 3 shaders. They're reused everywhere. Then in here we have our like loaders when we load an image or a mesh. We have all of that in here. We have a frustum culling plane, which we'll explain in a bit. And then we have our drawing calls and buckets, which I'll also explain in a bit. Lastly, this is the main function in here. It's called render word. I just refer to it as word. This is where D3D is initialized. We also have a pointer to our shared stuff here. We have our shaders, our rendering buckets, and then an array of all of the meshes that we load into the game, and also the textures. And you'll notice, like I said, it's a C style C++. We just, since we pre-allocated everything at the start, we can just make flat arrays and just use them. It's that simple. Then we have our public functions. We have our initialize for DirectX 11. We have our render function, our loaders. These also can count as loaders. You'll see in a bit, and just one resize function, and that's it. This is all the stuff that can be called essentially outside this file, which gets called in the platform layer in our game loop. We call our render or debug render here. And so the CPP itself is just a bunch of DX11 stuff. So yeah, this is where we initialize our DX stuff, like the swap chain and everything. It just is initialized here. It's called only once on startup. So the actual frame to frame things that happen, there we go, in our render function. It's just a couple of calls as well. So what we do is we begin the scene by just like wiping everything out and putting on a black screen, and then we render or rebuild our camera, just rebuilding our camera based on its rotation and position, and then we draw our entities. And the way things work here is that we project a plane, like a frustum culling plane, from the camera, and then we just check if we iterate over the entities and check if an entity is inside that plane, that essentially our view. If it is, then we render it. Of course, if it has a mesh of some sorts. Otherwise, we just skip it, and it's as simple as that. The way we render stuff is we push something called a draw call, and like we push the stuff that essentially the shader needs to know about into this call, and we push it into a bucket. And like I showed in here, we have 2 buckets. We have an opaque bucket and a transparent bucket. And here you can see already that we have some material flags that we're working with. Let me just go back into here. Our material flags are very simple. It's either lit, transparent, and it casts shadows. Transparent is actually only used like on 2D stuff, because this the engine's code just works out of the box for both 2D and 3D. So there are some things that might only be used with one of the kinds, which is this one, for example. So this is like for the little 2D guy that we saw. Like this is a PNG image, and the engine needs to know that it's a PNG in a way. For the actual 3D models or any other model, the way that transparency gets defined is, it's just if the alpha channel of the color is less than 1. So if we have any, so if you want like a semi-transparent object, you can just set the color of it, like the alpha channel of the color, into whatever you want, and it will automatically realize, okay, this is transparent. We're gonna add it to the transparent bucket. And then we have some simple shadows. Currently in the engine, I don't really have shadow mappings, but I wanted to have something. So like you can see these blobs here. This is essentially what gets created. It's just, if it's a 3D entity or like word, it will generate like a blob on the plane. If it's 2D, this is like more facing the camera. essentially like these, but it's just semi-transparent, so it doesn't look like it. Yeah, and after we've added all the draw calls, we just flush all of the buckets that we have. And flushing the buckets is just that we go in order. First we go with the opaque bucket, which just goes into all of the draw calls it has, updates like the updates the shader parameters for that call, and then just draws the mesh. And then we go into the transparent bucket, where it also draws this essentially the same function, just the shader parameters are different, and it draws all of the transparent entities. Then we draw the particles, which have their own shader that is just like a billboard facing the camera. And here, actually, for the particles, we essentially do one draw call for all of them. Like all of the particles in one emitter are drawn all at once. We just like pass the count, and then actually, if I just go into the shader immediately, you can see that it calculates all of the camera stuff, the camera and position. It calculates it inside the shader. So all of the like calculations go into the GPU side rather than the CPU. But we'll go into more of that when we talk about particles. And lastly, we flush our UI bucket, which also has, like I mentioned, its own shader, which is just a simple like orthographic, always on top shader. And the way that like UI elements go is that it's just like first come first serve. So the first one added to the bucket is the first one that gets drawn. This is what allows us to essentially put like text on top of a cube, or like in a button here. And yeah, that's essentially the renderer in summary. Of course, there are a lot of more details going on here, but this is what happens every frame, and all of the shaders, again, they get initialized in our first init function. And yeah, that's the renderer. Okay, so next thing in the documentary is our shared stuff, which I already actually explained, so we can skip over that. And then, yeah, our memory. This is really important. I already talked about it in the platform layer, but essentially we have this arena system where, there we go. This is the struct that like has all of the memory that we need in the whole engine. And like a memory arena is just it's just a block of memory with a certain size, and every time we use it, we like increment the used amount, so that we know when to stop or when we've like reached the limit, which never happens, by the way. And then we have these helpers for convenience, which all lead to the same function, this arena push size. So the way it works is that, for example, here we wanna create like the game state, and for it to be permanently in the game while the game is running. So we just say, okay, we're gonna push this block of the size of the game state into this arena, increment the used size, and that's it. That's literally it. So the next time we add something into the same arena, it's just gonna add it in front of what we've already added in that block. And that's all we do. So we have I have three kinds of memory arenas here. Our permanent arena is what gets created at the start, and it's always there. It never gets deleted until the game stops running. Our scratch arena, which is something handy. This is what we use instead of heap allocation and dynamic allocations if we need to do any of that. Like when we're loading our images or textures or meshes, we need to create something on dynamically, essentially. So we just use this scratch memory block, and every time we use it, at the end we just reset it here, and we reset it by just like moving the used block all the way to the back, so that the next time something uses the scratch memory, it's gonna override it, essentially. Again, so nothing is actually being deleted, it's just things are being reused and overwritten, and that's why like nothing crashes because of memory. And lastly, we have our level memory, and by the way, these are like the sizes. You can change them as much as you want. And yeah, like the level memory, it's something also that gets created when we start here. but then every time we load or unload a level, it gets like reset and reused. So there we go. We just like zero this thing out, which is just like setting the memory of it to 0, literally, and then we reuse it or use that block again for the next level. And that's how memory works in the engine. It's really straightforward. So the next bit is our custom assets or like file formats in the engine. So it didn't take much time to realize that loading a PNG or a JPEG or whatever, these files have like probably have big sizes, multiple megabytes minimum sometimes. And so what I decided to do is create a tool that is external from the engine. It's not at runtime. You run this tool offline, and what it does is it converts all of the like normal asset types into a custom file format that the engine reads. And this is what I call the Fado converter. So if you go into here, let's go all the way down to our main. This is its own CPP file. This gets triggered from a script. Let's just go into engine, tools, Fado converter. There we go. So yeah, this file gets compiled here, and then the way that things work is that for each file format that we have a loader for and support in our engine, we have a function that converts that type into our custom asset type. So we have like a simple asset dispatcher where you have an extension, and that extension is associated with a function, and the function just like takes only the data that we need from, for example, a PNG file. For images specifically, we're using STBs. We're using a third party that is STB BC3 compression, which just compresses an image file, and then we compress it again with LZ4, which is also like an open source compression framework, and then we pass that into our own custom headers. And this is the header where all like our custom assets are defined. So each type of asset has this asset header, which is shared between them all. It has the type, the version, and then each file format has its own header. Like the image has its own, the models, the 3D models have their own, the fonts, the sound, etc. And so we just simply write that stuff into the file, and this is what becomes a .if something file format. And I can show you a live example actually. So if we go into our engine, so yeah, we have an asset source and an assets folder. The asset source is where everything is. So like if I go into the textures, you can see the actual images, the JPEG, the PNG images, and these get cooked and placed here. And this is what actually gets used and exported or packaged with the game. Our, like, for example, if image, our if font, and all of that. And so, for example, let me just delete all of the textures here, okay? We are going to go into our tool, and I'm going to cook the assets. Yes, I do trust this. Ooh, interesting. Oh yeah, of course, first we need to actually compile the tool. So this batch file should do it. And now that we have our exe and everything, we can cook the assets. And you'll see that, hey, it's cooked this asset, blob.if image, and it reduced its size like drastically. And same for almost all of the other textures. And now if we go back and check our assets folder, textures, you can see all of them here, and these are what actually gets loaded and used in the game. And yeah, this is how the assets work. So we'll move on to the next part, which is our entities and transforms. Okay, so our entities, I don't know if this is what you would call an entity component system. It is essentially just a simple entities and like components arrays with handles. This is how the engine works. And right now I don't really have much components, so That's why I don't know if you can call it that, but the name doesn't matter really. The way things work is we have this one entity struct, which is shared between 2D and 3D, and an entity is essentially just a mesh, if it has one, a material, and then like for only 2D we have like sprite animation related stuff. And then we have this entity table with all of our entities in the engine. This is all of the entities that will ever be created while the game is running. And so we access entities in this array with specific handles. So if you noticed in our level, I had like, for example, in our 2D level, let's actually show the 3D, we have like these handles in the level itself. And what happens is that when we spawn them on init, we just assign these handles here. And so whenever like I wanna change the cube size, I would just access it through that handle. And for simplicity, the same handles are used for the transforms. Transforms are just vector 3 position, scale, and a vector 4, which is a quad, literally just a vector 4. Equatorian. And they use the same handles because, in my case, all entities actually have transforms here. And yeah, when we spawn an entity, we're not really creating anything. We're just saying, hey, give me the next available handle in this entities table, and we're gonna take a pointer to that and just assign our stuff into it. Again, no deletion, no creation, just reusing already existing stuff. And lastly, the material, which we already kind of touched upon in our renderer. A material is a color, a texture handle, and some material flags. Yeah, these are the ones like I mentioned before. And it's as simple as that. This actually brings us back to our level. So when we load and save and load entities, saving entities, we're just writing like the position, the rotation, the scale, and everything inside the entity itself, like the material, the mesh, all of the actual entity struct. And then we're just manually writing the position, rotation, and scale. We write it into this custom struct here, which is just like an entity and its position, and that's it. When we load a level, we call its init, so everything is spawned the same way. Like for example here, this is our order of spawn, of spawning objects. So when we init a function, we spawn them again, and then if we have a save file for that function, we just override the position, like the transform and the entity's values if we've changed them in the level. And that's one thing. Order is really critical here and important. So we have like the order of these, not really these, the order of spawning stuff here. Alright, so order of things. Funnily enough, in my first take, I found a bug when I was about to show the example. So I fixed that, and now... Okay, so there are actually two things. Okay, so there are actually two areas where order is important, but one is slightly more critical than the other. The first one is here, the level. So by default, this is the layout of our cubes, our entities, and their colors. And if we go ahead and save that, and then exit, and then if we, let's say we switch the position of just setting things up between the first and the second to last. So you can see like the rotations kind of changed. The textures are still pointing to the same thing, so that didn't change, but like the rotation itself of some of the entities did change. And that's because we're initializing these in order. So this will take, like for example, this will take 0 handle, this will take 1, 2, 3, and so on. And when we're actually loading the level itself, like I showed before, we're iterating over the entities based on their count. So we're going just from like 0 to, let's say, 10. And so what was in the previous level a 3, if it's now 6, then something changed, which will update the position of things. But the more important one is actually loading the textures and the meshes. So in our platform layer, we have this function, load assets, which just literally loads all the assets that we need in the game at startup. And so, for example, here's where things can be critical. So let's say our white texture which is just the default color texture. Like if you want to add just a color to an entity, you add the white texture and then you add a color to it. So if I switch these, let's see what happens now. You can see a lot of things actually change. First of all, our infinite plane is now white because like the position of the grid texture was third. Our transparency is also interesting now, and our colors are kinda screwed. I think they're using the Skybox texture or some other texture. Anyway, point is, order is important in these things. So, I mean, while you're prototyping, it's okay, but once you have like a level set up and ready, you should keep in mind that if you want to add some things, just add it at the bottom of your asset loads or at the bottom of your initialize function of the level. When it comes to memory-wise, order doesn't make any of a difference because they're just in the same array after all at different indexes. So always add things at the bottom if you have a level and you want to keep everything as it was. But yeah, this is how things are loaded and how entities work. And now we are going to talk about some of the subsystems in our engine. First thing first, the big boss, our collision system. Alright, so our collision header is in the engine, but since collision is mostly used in the game, we place the implementation in the editor. And the reason I have these like separations is because I'm using collision stuff for the debug lines that you saw earlier. Alright, so the way things work in here is that we have something called our collision world, and this is just everything that the collision system needs. So we have some collision pairs, and then an array of something called contact info. And the way things work is that each frame we have three main stages that the collision system goes into, and we can see that in any of the levels. So if I go into our update function, you can see there we go. So you can see that we have these three steps here. The first is called collision update, then resolve, and then reaction. And the update itself has three main parts as well. So first, we need to build our axis aligned boxes or like oriented boxes, and this happens for any entity that has that manually added a collider. So for example, here in our in our begin, we're adding colliders for the entities that need collision. And so here we just we always build axis aligned boxes because they're the simplest and they're used in our next stage, which is the broad phase. But it's worth mentioning that if an entity is rotated, it's also optional. Like, I can change this, but for now, if an entity is rotating and actually has a collision, then we also create so in the broad phase, we divide our world into like grid cells, huge grid cells, and then in each cell we save the entities that are in that cell as pairs. This allows us to drastically decrease the amount of collision checks that we need to do, because otherwise we'd be just comparing every single entity to every other single entity, which is unacceptable. This way we can easily drop like from thousands of checks to hundreds. So we divide the world into into bigger cells, and in every cell we check the pairs only in that cells against each other, which is what happens in our narrow phase. This is where we take all of the pairs and then we calculate the collision between them. We check how much they're overlapping, and we save all of that in our contact info. So we save which entities are colliding, and like the overlap and penetration details. And now with that populated, we go into our other stage, which is the resolve. And here is where things automatically in the engine gets pushed around. And this is what I was mentioning when I talked about the debug colors that we have here. We have different let's go here. So yeah, we have currently these flags for our collision. A trigger is something that doesn't get resolved here. This is only for like custom game mechanics that you need. And then we have this order. We have a static, a kinematic, a dynamic, and a physics. 2D is used for only 2D levels, and that's because there we go. When we calculate like the cells, it just calculates x and y instead of x, y, z. So just make things simpler for 2D. But these are what the resolve section relies on. And the way it does it is that it checks the pair of entities and assigns a mass value to them based on their type. So like static is the heaviest. It cannot be moved, for example. Dynamic is the lower than static and kinematic, and then physics is the least, like the lightest. And based on that, we decide which entity is gonna get pushed back and by how much. And that's the collision resolve. That's how things here. I'm dynamic and this is dynamic, so we are both kind of getting pushed. This is static and I'm dynamic. It's not getting pushed, it's only me getting pushed. And so on. And the last step is the custom game mechanics. This is whatever you want to do in your game. For example, in our 3D level, I'm checking if anything is colliding the camera in this frame, then I want to play a sound effect. An example I wrote in the documentation is, for example, if you want to do something when the camera is colliding with, for example, the Fado cube or whatever, you can do whatever you want. And also here is where you can check the triggers if some trigger collider was overlapped, and all of that. And that wraps up collision. Next is UI, and you can tell in the documentation that I was losing my sanity when I started adding memes into the documentation. And yes, ladies and gentlemen, we created a UI system from scratch. And it's actually much simpler than you think it would be. So yeah, let's dive into that. Alright, so there you have it. This is our UI system, plus a shader in the renderer like we showed before. A UI element, or as I call it, a UI command, is just a rectangular, a 2D position, width and height, UV coordinates, if we're using a texture, and then a color, which is similar to any of the other entities. Like here, a color is added as a tint because we have a texture. If we don't have a texture, then it's just a simple RGB color, and that's it. It's almost an immediate GUI thing, because in every frame that we want to add UI, we just say, hey, add this thing. So for example, in our game, every time we're pushing a bunch of buttons here, and buttons, by the way, are just a rectangle and with some smaller rectangles on top of it. These smaller rectangles are are our font, our letters. So yeah, we're kind of spiraling. Everything is every step is making us go into another subsystem, but this is how things really work, so we'll just go with it. So yeah, for example, this button here, we're just adding a rectangle with some colors and a texture, and then we go into our font system here. Adding a text is we're just going into our font atlas, and based on the text that we have, it jumps into like the correct position in that atlas. And if anyone doesn't know how fonts really work, because I actually learned this here, so this when you open a font file, this is what you would call an atlas. So for example, this font supports all of these characters here, and then when you want to actually write stuff, you navigate through these letters. And because this is just ASCII, if I write, for example, A, it will know that it's in this position of that texture. So it will grab this little cube here as a PNG, and this is what we add into our button. So again, when we add text to the button, we're just iterating over the text letters, and for each letter we're adding a small button. So for example, our button here is 1 rect, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it's in total 12 rectangulars that were added into our UI bucket. And it's as simple as that. Then we have in our game, for an actual button, we have our custom logic that we check the mouse's position. Where we check the mouse's position if it's inside the rectangular's bounds. If it is, then we know we're hovering over a button and all of that. And lastly, for controller, we have something called UI navigation state, which is just literally an index and the number of elements we have. So, for example, in here, this is element number 0, 1, 2, and 3. Let me put this full screen. And if I just plug my controller, you can see that we're navigating one by one, and I can even wrap around. So for example, this one is element 0, and then we're just, when we navigate down, we're saying increase the index 1, and so on until we reach the maximum count, which is 4 here. And then we can either wrap around or we can make it just stay at the last one. And yeah, the positions of things, it's just we assign a position to the first, for example, to the first button here. Let's see, where's our update UI? There we go. So yeah, we're assigning this position, and then all of the next buttons add like a relative offset to that first button. So for example, let's just say I'm gonna just change this to 0, 0, which is actually, I think, what's in the demo. So now if I click P, it's all the way at the top here, 0, 0, and all of these are still relative to that first button, which make things really organized. And yeah, last thing for the text itself, I added some helper that calculates or measures like the width of the text based on how many letters there are, and based on that we can make like the position relative to the rectangulars, and that's how I'm kind of centering the text of the buttons inside the rectangle. And that sums up UI in the engine. Next is sound, and as you saw in the showcase, we have 2D and 3D sound. Now, the way things work and the way I try to do things in this engine is to have things be a platform agnostic. So the plan is, if you ever wanna implement or work with this engine in any other platform, you should only have to change the actual platform layers, the Win32 platform layer, and maybe the graphics API if you're like working on console or something. And with that in mind, we have our Fado sound file, which calculates everything and mixes all of the sounds and like the position of 3D sounds and all of that, and passes it at each frame to the platform layer, where it can handle the sound based on the in its own implementation. Like for example, for Windows we're using Xaudio 2. So the way sound works here is, first we have this sound manager that lives in the game state. The sound manager has a pointer to what we call a sound asset bank, which has all of the loaded assets. So all of the sound assets that we load, all of the audio files essentially, what was generally a wave file, and then we have the instances. So for each sound asset in here, the actual instance in the level that is playing the sound is in here. And then lastly, how many instances of that one sound is being played right now. This here is used so that I can cap the amount of times one specific sound can be played. Now, the sound buffer is just the wave data that we load from the wave file, and our channels and sample rate and count. It's just what you need for what represents a sound, and then we have the minimum and maximum distance this sound can reach to, and then an index to a voice slot in our platform layer where the 3D sound actually gets outputted or processed into. And so for 2D sound, each frame we have to give the platform layer something called a sound output, which is the total mix of all of the samples, the 2D samples playing in this one frame. Let's check this out. So this is what the sound output is. It's just mixed sample and how many samples are there. And the way that we do this is that in every frame we iterate over our samples that are playing right now, our 2D samples that are playing. We check, we increment the cursor and check if we reach the end of the sound audio of the sample or not. If we did, if it's looping, we just repeat it. Otherwise, we stop it. And given that we're still playing the audio, we calculate the actual left and right channels, and then we just add that sample to our mixed output sample. And then in the platform layer, we simply copy our samples, and then we just pass that sound buffer into our X audio to source voice. And that's how 2D sounds are played. Now for 3D sounds, what we're doing essentially every frame is just updating, checking if the position needs updating. And that's usually the case if a sound is attached to an entity. But most of the updating really happens in the platform layer. Yeah, and yeah, the calculation itself is distance and all of that is all relative to a listener that we have, which has a position forward and up. This is, in our case, for example, in the 3D level, it's our camera. So in every frame, we're checking the distance from the audio source to the camera, and based on the camera's forward and up, we know if it's to the right, to the left. Based on that, we can calculate the attenuation, the pan, all of the values that we need to actually represent what would look like a 3D stereo audio mix. And this is what we pass for that specific 3D audio voice. So in our platform layer, we have an array of voice slots for 3D sounds. And the way I understand this is in X Audio 2, you can't really mix 3D sounds like 2D. So we have a voice slot for every 3D sound. And that's it. That's how sound works in our engine. Next bit is the particles. The particle system. Our particle system. This is the main struct that gets used when we actually create a particle emitter, which is essentially an array of actual particles. So if you think about it, this whole thing is a particle emitter, but each one of these is one particle. Then we have our particle attributes, which are a range of values that one particle can have. So if we go into our particle struct, you'll see that it has a position, an end position, or an end offset position, velocity, age, all of that, a size start, a size end. These values are assigned when we create a particle using these curves. And the way that it works is that we have, in a curve, we have something called a range. A range is just a struct of two of the same value. So like a float range is just two floats, a min and a max. And what we do is, for example, if we want to spawn a particle here, we want the position to be, for each particle, we want the position to be, for example, between 0 and 1 in the x-axis. So each particle will get a random value between these two ranges. And this is exactly what allows us to have this scatter effect. So like each particle here rolled a random end position between, for example, this point and this point, and that's why we have this randomness here. For this example, the colors apply. So we're just picking a random color between some green and purple color, and that's why each particle here has a different color. And so yeah, when we create a particle, you can either assign it to be looping, or it's just one burst and then nothing happens afterwards. When you update it, it mainly updates the lifetime and and just like lerps the attributes if they had ranges, and like updates the position, the color, all of that, if you actually had any of that as a range. And to show an example, currently I'm reusing one makefire particle function that I made just as a helper. And so, for example, right now we're saying the start position is always going to be 0. Okay. Of course, that's relative to the entity it's attached to, because that gets updated every frame. But our end position here has a range. So if I completely delete this, or like completely delete this range, and instead just do as the start. Oops. Okay, if we do that, I assume that now all of the particles will go in one direction. Yes, as you can see. So it's completely optional. You can have all the particles follow one line. This might be good actually for like this actually can look good if we want to move the entity, and this is like a trail to it. But yeah, same thing works with all of the other attributes. So our color, I'm currently having a random value between red and orange. Let's say freaking turquoise. Look at that. That actually looks good. It's like a blue flame. Nice. And yeah. Lastly, like I mentioned in the renderer, we have our particle shader that draws each particle emitter with one draw call. And that's it. Now, almost the last thing is our sprite animation system. Now, if you look at Pac-Man, original Pac-Man, this game, way back in the 80s or whatever, or whenever, had animation of some sort. And if you look at this beautiful game here, oops, if you look at this game, which is Hades, if you're unfamiliar with it, Hades, one of the most top, highly rated and most selling games, actually uses sprite animation. If you didn't know. So all of the 3 models in here are rendered in Maya or some 3D rendering software, and then they're brought each as like frames into one sprite sheet, and then that's how the engine actually animates them. And so, for the sake of 2D and actually 3D, because making a 3D skeletal animation system is it's gonna be another project on its own, I decided to add a sprite animation system. And the way it works is really simple. It's actually really similar to the font system. So usually you have also an atlas for your model, or for your model that you want to animate. So for example, for our little Fulefila here, we have this texture. This by the way was created in Sprite. So I made this sprite sheet, and then let's see how things work in the code. Okay, essentially a sprite sheet has a bunch of clips. If we go back to the image, this is a clip, let's call it idle, and this is a clip, let's call it running or run animation. So a sprite sheet has a bunch of clips, and then each clip has an assigned start frame and how many frames it has, how many frames per second for the animation, so like the animation speed, and then if it's looping or not. And that's it. Every frame, we just update the animation state, which is we check which clip we have and how far along are we in it. And then if we finished what is counted as one frame in that clip, then we move to the other frame right here. And that is it. In our actual game, the way we do things is, for simplicity, you can make a custom enum. For example, I made an idle and I run enums here. Then, when we want to begin the game, we add our clips. So in our image again, I should keep this open. So in our image here, our first clip is from frame 0 to frame 2. So these two, all the way over here. So it starts at 0 and it has 2 frames, and our second clip starts at 2 and also has 2 frames. And this one plays much faster than that one. And then when you actually want to update the game, so for example, after we've updated our game and we've updated our player's position and all of that, what I'm doing here is just checking if we've moved at all, if there's any difference between our new position and old position. If we've moved, then we're running. If we haven't moved, then it's the idle. And since we assigned these handy enums, it's much readable this way. And the result of that is what you can see here on the screen. And the beautiful thing is that you can use this in 3D as well. There are a lot of 2.5D games out there that have 3D environment but use 2D sprites to animate their characters. So it's really handy and just gives some sort of life to the characters, to the engine. Okay, another simple thing that I forgot to mention is actually the plane and the skybox. So the plane is it's literally an infinite plane with a texture that I made, and it follows the camera's position on the X and Z axes. And the skybox is actually very similar. The skybox is just a cube with a certain texture and essentially flipped UV coordinates. So it looks like the texture is displayed on the inside instead of the outside of it. So the skybox is simply just this cube, but very large, and that's it. The texture is something I got online. I have the reference in the engine, and that's it. Yeah, magic. And yeah, that sums up Fado Engine. You can check the documentation, like I mentioned, for all of the details. You can download the demo on HIO, and you can download the engine on GitHub. And please do let me know if you tried it out. You can reach out to me here. I should probably create a contact me page, but you can send me a message, and you can hire me if you're looking for someone. This project was really, really valuable to me, and I learned a lot from it. It's really amazing when you create things from scratch. It removes all of the magic layers that you have when you're working with an engine or something. And if you do want to go back and work with any of those engines, you just have a much wider understanding of how things work underneath the hood, which is really awesome. For resources, I have some resources here. I can't recommend this enough. It's called Handmade Hero. It's a live coding series where a legendary programmer called Casey Muratori creates a game from scratch. This is actually where I started. So if I go into my GitHub, you can see this older project, which doesn't really do much, but this is all created from scratch. And I stopped working on that project to work on my actual engine, but it was the basis of what made Fado Engine. So I can't recommend this enough. Rastric for DX11, it's a good starting point for anyone interested in DX11 graphics. And there's Wookish podcast. It's more like technical game programming stuff. He interviews industry veterans, and you can learn a lot from just hearing about their stories and how they make stuff. And yeah, my next plan is to actually make a game with this engine, which hopefully will happen soon. The day I'm recording this is a couple of days away from the GMTK Game Jam. This is where I actually participated in that jam a while ago, made this game that is unfortunately lost. I don't have the project files anymore, and it's unplayable on modern machines. But yeah, the goal is to make a game with this engine, and you'll definitely hear about it once that's done. And yeah, that's all I have for today. If you've reached this point in the video, thank you very much for watching and listening. I hope that you learned something or had fun. If you have any comments, suggestions, or ways that maybe things can be done better, feel free to send me a message or write a comment. You can also email me here. And yeah, that's all. Thank you very much. Have a good one.